Welcome. Let's take a look at concavity, what it is and how we can determine it. So that we say that a function is concave up on an interval I if f prime of x is increasing. Well, what does that mean? So f prime of x is increasing means that, in essence, the derivative of f prime of x is positive, or f double prime of x is positive. We say a function is concave down on an interval if f prime is decreasing. So f prime of x is decreasing, which kind of implies that we're saying that f prime, the derivative of f prime is negative because it's decreasing. Or we could say that f double prime of x is less than 0. Now, it's important to note that at points where the function, the second derivative changes sign, those can be points of inflection, provided those points are in the domain of the function. So let's take a look at an example. So let's look at finding the open intervals on which a function f of x is equal to x cubed minus 6x squared is concave up and concave down. We also want to consider, are there any points of inflection? If so, provide coordinates of those points. So to determine where a function is concave up or concave down, we need to consider the critical points of the second derivative. So we are going to consider the critical points of the second derivative. So let's first find the second derivative. So f prime of x is equal to 3x squared minus 6 times 2x, or more simply 3x squared minus 12x. Our second derivative is the derivative of 3x squared, which is 6x, minus the derivative of 12x, which is 12. Now we want to consider the critical points of the second derivative. So the first thing we need to consider is, where is the second derivative equal to 0? That means, where is 6x minus 12 equal to 0? Or 6x is equal to 12 if I add 12 to both sides of the equation. And then if I divide both sides of the equation by 6, that would be where x equals 2. Now, there is a second source of critical points that we need to consider, and that is where the second derivative does not exist. Well, my second derivative is a nice linear function, and it's defined for all real numbers. So there aren't any x values for which the second derivative does not exist. And so we make a little note of that f double prime is defined for all real numbers, so there are no critical points from the second derivative not existing. So now we need to test the intervals created by the critical points to determine whether or not the second derivative is positive or negative. And since there's only one critical point at x equals 2, that will divide the x-axis into two intervals. One interval is from negative infinity up to 2, and the second interval is from 2 on to infinity. Now what we're interested in is the sign of the second derivative in these intervals. So let's go ahead and choose some test values to determine the sign of the second derivative. So in the interval from negative infinity to 2, let's choose a nice x value like, say, x equals 0. So f double prime at 0 will be 6 times 0 minus 12. We're not interested in the number, we're interested in the sign. And that will be 0 minus 12, which will give us a negative value. So we know that in the interval from negative infinity to 2, the second derivative will be negative. Choosing a nice convenient value in the interval from 2 to infinity, like 3, f double prime at 3 will be 6 times 3 minus 12. 6 times 3 is 18, and 18 is bigger than 12, so when I do that subtraction, I will get a positive number. So we know that on the interval from 2 to infinity, that our second derivative is positive. So from this, we can determine that on the interval from negative infinity to 2, our function is concave down, and from 2 to infinity, our function is concave up. So we would say that the function is concave down from negative infinity to 2, and the function is concave up on the interval from 2 to infinity. So that answers the question about the open intervals on which the function is concave down or concave up. Now we need to consider the question of whether there are any points of inflection. Now, a point of inflection occurs at points in the domain of the function where the function changes concavity. So we see here that we had a point, a critical point at x equals 2, and x equals 2 is in the domain of the function. And we see that we do in fact get a change of concavity from concave down to concave up from the left side of x equals 2 to the right of x equals 2. So there is a point of inflection at x equals 2. And let's go ahead and find the y-coordinate that goes with that point, or that x value. So we have 2 cubed minus 6 times 2 squared. So that's 8 minus 24, which would give us negative 16. So there is a point of inflection, and that happens to be at the x value of 2 and the y value of negative 16. I hope you find this helpful.